Welcome to our series on electromagnetism. In this first part, we will explore how electric currents interact with magnetic fields to produce mechanical forces. This fundamental interaction is the cornerstone of electric motors, generators, and many measuring instruments. Let's begin by looking at the physical origin of this force. When an electric current flows through a conductor, it generates its own magnetic field around the wire. If we place this current-carrying conductor inside an external magnetic field, these two distinct magnetic fields interact. This interaction creates a physical, mechanical force that can move the wire or cause a coil to rotate. Understanding this force is key to understanding how electrical energy is converted into mechanical work. The magnitude of this magnetic force isn't random. It depends on four key physical factors. First, the current flowing through the wire. More current means a stronger magnetic field around the wire, and thus a larger force. Second, the length of the wire that is actually immersed inside the magnetic field. Third, the strength of the external magnetic field itself, which we call magnetic flux density. And finally, the angle at which the wire cuts across the magnetic field lines. By combining these proportionalities, we can write a single relationship. Force is proportional to the magnetic flux density B times the current I times the length L times the sine of the angle theta. Introducing a constant of proportionality, K, we get F equals K times BIL sine theta. In our standard international system of units, we define our units such that this constant K is exactly equal to 1. This gives us our classic, elegant equation, F equals BIL sine theta. Now, let's formally define this term magnetic flux density, represented by the symbol B. We define it based on the maximum force a conductor can experience. Specifically, it is the force acting on a wire of unit length, 1 meter, carrying a unit current of 1 ampere, when the wire is oriented perfectly perpendicular to the magnetic field. When the angle theta is 90 degrees, sine of 90 is 1, simplifying our equation to F equals BIL. Rearranging this, B is force divided by current times length, and its SI unit is the Tesla, abbreviated as capital T. Let's look closer at this unit, the Tesla. By definition, a magnetic field has a magnetic flux density of exactly 1 Tesla if a 1 meter long wire carrying a current of 1 ampere experiences a mechanical force of exactly 1 Newton when placed perpendicular to the field lines. This means 1 Tesla is equivalent to 1 Newton per ampere meter. It's a very large unit of magnetic field strength, as we'll see in practical examples. To find the direction of this force, we use a handy tool called Fleming's left-hand rule. If you hold the thumb, first finger, and second finger of your left hand mutually at right angles to each other, they represent 3 orthogonal axes. Your first finger points in the direction of the magnetic field, your second finger points in the direction of the conventional current, and your thumb will naturally point in the direction of the resulting mechanical force, or thrust. It's an easy way to remember how these 3 vectors relate in 3-dimensional space. Let's put this theory into practice with a concrete example. Suppose we have a conductor that is 10 centimeters long, carrying a current of 5 amperes. It is placed inside a magnetic field with a flux density of 0.2 Teslas. We want to calculate the force acting on this conductor under 3 different orientations. First, when it is at a right angle to the field. Second, when it is at 30 degrees. And third, when it is parallel to the field. First, let's always convert our length to standard SI units, so 10 centimeters becomes 0.1 meters. Let's calculate the force for each case. For case 1, where the wire is perpendicular to the field, theta is 90 degrees. Plugging our values into F equals BIL sine theta, we get 0.2 times 5 times 0.1 times sine of 90, which gives us exactly 0.1 newtons. For case 2, at 30 degrees, we multiply by sine of 30, which is 0.5, yielding a force of 0.05 newtons, exactly half of the maximum force. Finally, when the wire is parallel to the field, theta is 0. Since sine of 0 is 0, no magnetic force is produced at all. Now that we understand how a single straight conductor experiences force, we can look at what happens when we loop this conductor into a rectangular coil and place it in a magnetic field. Building on our understanding of how a moving coil galvanometer operates, let's examine its sensitivity. First, we have current sensitivity, which is defined as the deflection per unit current, or theta over I. Mathematically, this equals BNA over K. To make a galvanometer highly sensitive to tiny currents, we can increase the coil area A, add more turns N, use a stronger permanent magnet to boost B, or use very fine hairsprings with a small torsional constant K. Next, let's look at voltage sensitivity, which is the deflection per unit voltage, or theta over V. Since Ohm's law tells us that voltage equals current times resistance, we can substitute current as V over R into our torque equilibrium equation. Rearranging this gives us the voltage sensitivity formula, BNA divided by the product of the torsional constant K and the total resistance of the coil, R. Notice how coil resistance plays a crucial role here. Now, how do we adapt a delicate galvanometer to measure much larger currents? We convert it into an ammeter. To do this, we connect a very low resistance, called a shunt, in parallel with the galvanometer. Because the shunt has a much lower resistance, the vast majority of the current bypasses the galvanometer and flows through the shunt, protecting the instrument while allowing us to measure the total current using parallel circuit rules. Let's work through a practical example. Suppose we have a galvanometer with a resistance of 4 ohms and a full-scale deflection current of 10 milliamps, and we want to measure up to 1 amp. First, we convert 10 milliamps to 0.01 amps. The remaining 0.99 amps must flow through our shunt. Setting the voltage drops equal, we find that our shunt resistance needs to be approximately 0.0404 ohms. Let's look at 2 more scenarios. In the second example, with a 20-ohm galvanometer and a 2 milliamp full-scale current, we calculate a shunt resistance of 0.0401 ohms to measure up to 1 amp. In the third example, we are given the shunt resistance of 0.06 ohms and need to find the maximum measurable current. By calculating the shunt current first, we find the total measurable current is 0.135 amps. What if we want to measure a large potential difference instead? We convert our galvanometer into a voltmeter. This is achieved by placing a very high resistance, called a multiplier, in series with the galvanometer. Since they are in series, the same full-scale deflection current flows through both, and the total voltage drop is simply the sum of the voltage drops across the galvanometer and the multiplier. Let's see how this works in practice. Imagine we want to measure up to 30 volts using a 10-ohm galvanometer that has a full-scale deflection current of 15 milliamps. Converting 15 milliamps to 0.015 amps, we set up our series equation. Dividing 30 by 0.015 gives 2,000 ohms for the total resistance. Subtracting the internal galvanometer resistance of 10 ohms, we find we need a multiplier of 1,990 ohms. Now, let's shift our focus to the fundamental physics of moving charges in magnetic fields. We know a current-carrying wire experiences a force equal to BIL sine theta. If we look at this microscopically, current is the flow of charge carriers with a drift velocity v. By substituting the microscopic definition of current and the total number of electrons in the wire into our force equation, we derive that the magnetic force on any moving charge is BQV sine theta. This derivation gives us a precise way to define magnetic flux density, B. It is defined as the force acting on a charge of 1 coulomb, moving at a velocity of 1 meter per second, perpendicular to the magnetic field. When the velocity is exactly perpendicular to the field, the sine of 90 degrees is 1, simplifying our force equation to just B times Q times V. Let's apply this to 2 examples. First, an electron beam moving at 100 meters per second perpendicular to a 0.04 Tesla field experiences a tiny force of 6.4 times 10 to the power of 19 newtons. Second, when a 50-centimeter metal rod moves through a magnetic field, the free electrons experience a magnetic force. At steady state, this is balanced by an electric force, creating an electric field of 0.25 volts per meter and an induced potential difference of 0.125 volts across the rod. This separation of charges in a moving conductor leads us directly to a fascinating phenomenon observed when a stationary conductor carrying a current is placed in a magnetic field. This transverse potential difference is known as the Hall effect, which we will explore in detail next. Let's explore how we can practically measure magnetic flux density using the Hall effect. We start with a thin semiconductor slice connected to a direct current voltage source, which drives a steady current through it. We also connect a voltmeter across the width of the slice, perpendicular to the current flow. First, we place this setup into a reference magnetic field with a known flux density, B0, making sure the field is perpendicular to the face of the slice. We record this initial Hall voltage reading as V0. Next, we move the semiconductor slice into the unknown test magnetic field, B, and record the new voltage reading, V. Because the Hall voltage is directly proportional to the magnetic flux density, we can easily calculate our unknown field using the simple ratio. B equals V over V0 multiplied by B0. Now let's look at how we calculate the magnetic flux density produced by current-carrying conductors of different shapes. For a long straight wire carrying a current I, the magnetic flux density B at a perpendicular distance r is given by mu naught I over 2 pi r. If we wind that wire into a circular coil of n turns and radius r, the field at the very center is stronger, given by mu naught Ni over 2r. Finally, for a long solenoid with n total turns over a length L, the magnetic flux density along its central axis is uniform and equals mu naught Ni, where n is the number of turns per unit length. An important detail to remember is that at the very ends of the solenoid, the magnetic field strength drops to exactly half of its value at the center, which is mu naught Ni over 2L. Let's put these solenoid formulas into practice with a concrete example. Suppose we have a solenoid with 2,000 turns, a length of 75 centimeters, and a current of 2.5 amperes. First, to find the magnetic flux density at the center, we use our standard solenoid formula, B equals mu naught Ni over L. Plugging in our values, we get 8.38 times 10 to the minus 3 Tesla. Now, what about at the ends? Since the field at the end is exactly half of the center value, we can simply divide our previous result by 2, or calculate it directly using 2L in the denominator. This gives us 4.19 times 10 to the minus 3 Tesla. Notice how straightforward this is once you identify the correct formula for each location. In this next example, we look at the interaction between a long solenoid and a small circular coil placed at its center. The circular coil has 10 turns and a radius of 2.5 centimeters, and its axis is perpendicular to the solenoid's axis. The solenoid has 750 turns per meter and carries a 2 ampere current. First, we find the magnetic flux density inside the solenoid using B equals mu naught Ni, which gives us 1.88 millitesla. Next, when a current of 1 ampere is passed through the circular coil, it experiences a torque. Since its axis is at right angles to the field, the torque is maximized and given by BINA. Calculating the area of the circular coil as pi times r squared and substituting the values, we find the initial torque is 3.7 times 10 to the minus 5 Newton meters. Sometimes a problem won't give you the current directly, but will instead provide the electrical properties of the solenoid. Here we have a solenoid with 2,000 turns, a length of 40 centimeters, and a resistance of 16 ohms, connected to a 20-volt power supply. Our first step is to use Ohm's law to find the current. 20 volts divided by 16 ohms gives us 1.25 amperes. Now we can proceed with our magnetic field calculations. At the midpoint of the solenoid's axis, the flux density is 7.9 millitesla. At the end of the solenoid, the field is halved, yielding approximately 3.95 millitesla. Always remember to check if you need to calculate the current first.
Let's look at a more advanced scenario involving mechanical equilibrium. A rectangular coil is suspended inside a solenoid, and they are connected in series, carrying a current of 3 amperes. The magnetic torque on the coil causes it to rotate, twisting its suspension wire until the restoring torsional torque balances the magnetic torque. First, we find the magnetic field at the solenoid, which is 4.52 millitesla. The magnetic torque is BINA. At equilibrium, this equals the torsional torque, K times theta, where K is the torsional constant and theta is the angle in radians. Converting 40 degrees to 0.698 radians and solving for K, we find the torsional constant of the suspension is 3.50 times 10 to the minus 4 Newton meters per radian.
In this problem, we aren't given the number of turns directly. Instead, we know that a wire of total length 157 meters is wound into a solenoid with a diameter of 5 centimeters and a length of 25 centimeters. To find the number of turns, we divide the total wire length by the circumference of a single turn, which is pi times the diameter. This calculation reveals that we have exactly 1,000 turns. Now, we want to find the magnetic flux density at the end of the solenoid. Using our formula for the end of a solenoid, we plug in our 1,000 turns, a current of 2 amperes, and a length of 0.25 meters, giving us a final value of 5.0 millitesla. Let's look at one final example, which introduces the concept of magnetic flux linkage. We have a solenoid carrying 10 amperes with 1,000 turns per meter and a diameter of 80 centimeters. First, we find the magnetic flux density inside, which is 12.57 millitesla. Next, we calculate the cross-sectional area of the solenoid using its radius of 40 centimeters, which gives us 0.503 square meters. Since we want the flux linkage over a 1 meter length, we use the 1,000 turns in that span. Multiplying the number of turns, the magnetic field, and the area together, we find the total magnetic flux linkage is 6.32 Webers. To wrap up our discussion on magnetic fields, let's review the key concepts we've covered. First, the Hall effect provides a highly reliable way to measure magnetic flux density by comparing Hall voltages. Second, we've mastered the formulas for calculating magnetic fields across different geometries, including straight wires, circular coils, and solenoids. Remember that the field at the end of a solenoid is always half of the field at its center. Finally, we saw how these magnetic fields bridge the gap between electrical quantities like current and mechanical outcomes like torque. Keep practicing these multi-step problems, and you'll find these concepts highly intuitive. Thank you for joining me.